the capacity of the rats to run on a treadmill, which is severely impaired in old animals, was improved almost 20% compared to what they were doing at the beginning of the study. 20% is a huge increase.
Hello and welcome to the Live Long and Master Aging podcast. We call it LLAMA for short. I'm Peter Bowes, and this is where we explore the science and stories behind human longevity. Today, some fascinating science and a discovery that has been described as an unexpected fountain of youth. A new study suggests it could someday be possible to reverse the aging process in the human heart. It involves cardiac stem cell infusions. And to find out more, I've come to the Cedars-Sinai Heart Institute in Los Angeles to meet Dr. Lilian Grigorian, who is one of the lead investigators on the study. Dr. Grigorian, welcome to the LLAMA podcast.
Thank you very much. It's my pleasure to be with you today.
Cedars-Sinai, known around the world, of course, as one of the main hospitals here in Los Angeles, known for its patient care, but there's a tremendous amount of research done here as well, isn't there?
Exactly. Basically, this was the reason why I chose this hospital, the Heart Institute, and this particular lab to come here 3 years ago, because it's completely pioneer in cardiovascular regeneration therapies.
And you're from Armenia?
I am Armenian, but I grew up in Spain, so I consider Spain as my second motherland.
And where did you train to be a doctor?
Actually, this was something that I decided when I was almost 4 years old, so it was my passion all my life, and I'm coming to this and still continue walking. It's my passion, my life goal, I would say.
So it was in your blood almost?
Yeah, exactly.
To do this?
Exactly.
And where did you go to school?
I started in Armenia, and at the age of 14, I moved to Spain with my family because it was a difficult time in Armenia. And for a familiar reason, my mother, she's a pianist, she was invited in Spain for a concert tours, so that was the reason why we moved there.
You were enthused by what this place, Cedars-Sinai, could offer you in terms of academic potential. That's why you came here?
Exactly. So actually about 15 years ago, when all this regenerative therapies surge, I saw that it's something that I'm very, very interested in. And I proposed at that time that once I got my cardiac formation completed, I have to go somewhere to be able to learn this field in depth. So I was looking very deeply, and I saw that this is exactly the place that I want to come, and I was very lucky that I was accepted here, actually.
So let's talk about this study that's actually made quite a lot of headlines over the last week. And when I hear about the fountain of youth and reversing aging, I am often instinctively skeptical because they are big claims. But I think in terms of this research, it may not be so far-fetched.
Actually, I agree with you. We have to be extremely careful in the things that we are doing and the things that we are saying. But what this particular research is coming to say us, that the thing that we initially thought, specifically the aging, we believe that aging is like the end of our lives, irreversible stage of our lives. And with this research, we are trying to confirm that that's not true. We can act and try to reverse, at least in some part. But anyway, as I said at the beginning, we are still working. We have to work a lot and very carefully and go step by step. But the results now show us that it's like we are going in the right direction, and we are finding, all that things that make us be sure, pretty sure that we can act on aging and try to revert it at some degree.
When you say aging, as it relates to an organ in the body, and in this case it's the heart that we're talking about, you're really referring to an organ behaving as if it were much younger than it actually is in terms of years.
Yeah, actually, when I'm now thinking about aging, I'm understanding that it's like a chronic disease more than irreversible stage. So, and what this chronic disease exactly is, for me, I think the main thing of aging is the failure of our body to defend ourselves. That's what's exactly going on with aging.
So this study, let's explain it and break it down. What did you initially set out to do and to investigate? What was the aim?
So basically, before coming here, I did a lot of clinical research and heart failure, and a particular type of heart failure, which we call heart failure with a normal pump function of the heart. It's very prevalent and very related with aging. So I worked a lot with patients with this type of heart failure who they have a very high mortality and morbidity rate, and the problem that we still don't have any approved good treatments for these patients. So I always was interested in this particular type of heart failure. And when I came here and saw the cardiosphere-derived cells and everything what was demonstrated with these cells in preclinical and also clinical trials, because these cells were developed almost 10 years ago at Dr. Marban's lab, I understood that this cell may be effective in this particular type of heart failure because they have all the needed effects that we need to modify in patients with this type of heart failure. So our initial goal was to try to treat the heart failure with preserved ejection fraction. So we started there.
And the cells that you're talking about, can you break that down for me?
So the cardiosphere-derived cells are basically heart progenitor cells and stromal cells. What are these progenitor cells exactly are? Heart progenitor cells are cells which are able to be transformed in any different type of cells. That means that they can be transformed in cardiomyocytes, which are the main functional cells of the heart. They can be transformed into vascular cells, to the fibroblasts, any kind of cells. So these are the progenitor cells.
So these are stem cells?
Not exactly stem cells, but they are very similar and share many characteristics with the stem cells. The basic difference is the stem cells are able to proliferate indefinitely. Progenitor cells cannot do that, but they can be transformed, as I said, equally to the stem cells in different type of cells.
So this was a study that you did, an experiment that you did with rats.
Exactly.
Can you explain what you did?
So what we did, we took very old rats, which I would say, to make it easier to understand for people, it's like equivalent to 70 years old humans. First of all, we checked that those rats had the heart dysfunction that we want to treat, so we confirmed that.
And for a rat, that's about 22 months old?
Yeah, exactly. It's about 2 years old rats. So initially, we confirmed that age rats present the heart dysfunction that we want to treat. And after that, we just allocate part of that old rats to receive cardiosphere-derived cells, and part of the rats to receive just saline, which is the effect of saline is placebo. And we compared them with young rats. This is what we exactly did.
How many rats and how big an experiment was this? Over what period of time?
The experiment was accepted in terms of preclinical research. We used about 12 rats in each group. This was the sample size. This is completely accepted for this type of studies.
And so where do the cardiosphere cells come from? They come from younger rats?
Exactly. So as the goal was rejuvenation, we hypothesized that we need to use young cells in order to rejuvenate an old organism. So we go to the extreme younger age that we have. That's the neonatal rat. So we took the cells from the neonatal rat hearts, expand them, and then inject them into the old rat's heart.
So these are rats, these are baby rats in the very early stages of
Exactly.
formation.
And not only because they are very young baby rats, it's because something very interesting is going on in exactly that time period with these baby rats. That baby rats are able to regenerate almost completely their heart. That means that if we induce some lesion in the heart of these very young rats, that heart will be completely healed in terms of 1 month.
So what you were hoping to achieve was essentially mimic that regeneration in the older rats.
Yeah, that was the principle of this study, yeah.
So what happened?
So what happened, it was very exciting actually, because first of all, we found that we are improving the heart function, which is the most important, because many times we see studies which demonstrate structural changes in the heart. But if we have structural changes and that structural changes are not followed by functional improvement, that's, we have to question more that. But in this case, we very carefully first evaluated the heart function, and we saw a very significant improvement in terms of the heart function that we were trying to improve. And these changes were approaching our old animals to the younger control group that we used. Second, that functional changes were in accordance with the structural changes. And also at the last point, we tried to demonstrate that all that things are really a true rejuvenation, not other type of effects. So we went directly to the markers of rejuvenation, and we confirmed that what we see, that the old heart is getting younger in those senescence-related markers. And probably we can conclude that the consecutive structural and functional changes are the consequence of that heart rejuvenation.
And when you say the heart is functioning better, in what way is it functioning better? Is it pumping blood in a more efficient way? What is it doing?
Yeah, so that heart failure with preserved ejection fraction, what means exactly preserved ejection fraction? Ejection fraction is the pumping capacity of the heart. So in old people, usually the pump function, the capacity of the heart to pump blood is preserved. What's going on is that the heart is very fibrotic and stiff. So it cannot assume all the blood with a relaxation of the walls. So the pressure inside of the heart is getting very high. And this high blood pressure going backward to the lungs, causing dyspnea and all the symptoms that the patients have with this type of heart failure. So what we saw that we are able to reduce the stiffness, functional stiffness of the heart, and we make the heart relaxate more fastly than it was doing before. This is basically the changes.
And there were other benefits as well for those rats. They had more stamina, I understand.
Yeah, that was the things that we didn't expect initially, but we noticed them pretty soon after starting the experiment. It was something completely unexpected. As you can imagine, we are, Heart Institute lab working on cardiac regeneration and detecting that the fur of the rat is regrowing faster. It's not something that we, target from the beginning, but we saw that. And when we saw that, we went and checked that carefully, and we confirmed that. And not only hair regrow, but we saw a broad systemic effects. First, and probably one of the most important, is that the functional capacity, the capacity of the rats to run on a treadmill, which is severely impaired in old animals, was improved almost 20%. Compared to what they were doing at the beginning of the study. 20% is a huge increase.
And so you took baseline measurements of their ability to run on a wheel, to cope with activity.
Exactly.
And in terms of their fur, their hair growth as well, you measured that before, after?
No, hair regrowth, this was completely not expected. We just, after 1 week of shaving the rat, because we are shaving them for the surgery, 1 week later, when I was reevaluating the rats, because we have to reevaluate them almost on a daily basis, I suddenly noticed that something is weird is going on. So I saw what's going on. It's like they have more hair. And when I saw in some rats, I brought all the rats and I looked them carefully. And after I followed that process regrowing for 2 more weeks, so after 3 weeks, I analyzed that and I confirmed that we see important differences between treated with cardiospheres and non-treated rats.
That's quite remarkable if
Yeah.
you think about it, because clearly if you, and we're
Yeah.
not at this stage yet, but if we extrapolate this to human beings and hair loss and hair growth, there might be
Yeah.
some people, some men especially, who might be
Exactly.
interested in that.
When actually it's, I understand that it's something very exciting. In fact, when I was presenting the initial results of the study at UCLA, I noticed that people are more interested in the hair than in the heart even. So I understand that, yeah, of course.
So multiple benefits. Have we covered them all then? So increased stamina, increased performance of the heart, hair growth as well?
Yeah, so we we looked into the renal function. Renal function is very related with the heart function as well. So we saw some trend toward improvement of the renal function as well. We analyzed, we know that aging is related with body weight loss, which is called sarcopenia, cachexia. So we saw that animals which we treat with cardiosphere-derived cells under that surgical stress lose less body weight compared with the control group. And also trying to put all these changes together, we analyzed a systemic inflammation. And we saw that we positively modulate systemic inflammation in the rats.
And what's the significance of that?
That's very, I think this is one of the common things related with the aging. Aging is causing chronic low degree of inflammation in the organism, and this chronic inflammation may have a lot of, bad consequences in different organs.
You noticed that across different organs in the rat?
And
the
this
lack of
inflammation we analyzed in this study in the blood. So we analyzed, we collect blood at the beginning of the study in all animals and at the end point of the study, and we saw that the differences are significant. So we are modulating, we are decreasing the levels of inflammatory markers in the blood of the cardiosphere-treated rats.
So it seems that there are widespread benefits, certainly to those aging rats, those very old rats. The results suggest that the benefits are very significant. What's the next stage in the research?
So this was just the first study, and we made this discovery in this opened, a new pathways that some of them we already started, and some of them, unfortunately, I don't know if we will be able, but we will at least try to do that. I would say that
Because that's what science is, isn't it?
Exactly.
It'll take you down a road that you don't expect.
Exactly. That's the nice thing. This is what I exactly love to do, when you discover something completely unexpected, and this just open, many ways. So one of the important discoveries and questions that we had in this initial study is how exactly cardiosphere-derived cells rejuvenate. We know that many of the effects of the cardiosphere-derived cells are because of some very small vesicles that these cells secrete. Some of that vesicles are called exosomes, the smallest one. So we tried to check if that's true, that particles, that secreted vesicles, are carrying all the necessary compounds that we need to rejuvenate. And I mean RNA, ribonucleic acids, protein, lipids. So we did very initial studies, which are already published, and we saw that yes, it's reasonable for us to think that it's not the cell by itself, but it's the particles, the vesicles that this cell are secreting are the messengers of that rejuvenating effect. So now we are working on that, and hopefully very soon we will be able to publish our next next study. I'm even more excited about that next study than the previous one.
And of course, the question, the obvious question is always, can we look forward to perhaps human trials and the same sort of science applying to men and women with aging hearts?
Exactly, but as I told at the beginning, we have to be very careful. It's not like taking a simple drug and block a single pathway. We are using mixture of many things inside, let's say, that vesicles. So the effect that we are inducing are multiple. Some may be beneficial, other may be harmful. So we have to go slowly and checking the safety. At this point, I can say that we are pretty sure that we are safe, and we have a lot of patients treated with cardiosphere-derived cells, almost 100 patients, and we had no safety issues. And another important thing, because safety is something that I'm really concerned before talking about human studies, that we also checked one of the important points in cell therapy, which is the cancer risk related with the stem cell therapy. And I'm very happy to say that we did a specific study, which is already accepted and will be published also soon, that these cells seems very safe, even for the cancer. So for
and that was a study using rats?
That cancer study used mice and rats. We used in different rodent models to confirm that it's something general, not only specifically related to some animals. So for human trials, what you asked me before, we are moving forward, but very carefully. So hopefully, I think in some years we will be able to get there.
And listening to what you say about being cautious, a key question is always, if something appears to be very beneficial in the short term, what about the long-term implications of whatever treatment it is, whether it involves cells like this or something else? It's very difficult in a short clinical trial to look down the road, 5 years, 10 years, that perhaps there could be some negative implications.
Of course, you are completely right, but you understand there we have reasons to, it's impossible to, it's very hard to make those long-term trials, but I completely agree with you, and especially in stem cell therapy, you see that we even cannot get, the required number of patients. All stem cell trials are very small. And when you are using just 20 patients instead of thousands, which other, clinical trials are using, it's very hard to demonstrate. The differences between the groups should be very huge to get that statistical significance that we need to approve something for human treatment.
Are there ethical issues to consider here as well when you're harvesting cells like these?
We work with cells which we don't have any ethical issues related with the cells that we are using. But anyway, one of my goals is try to simplify this, to make it easier, because the source of the cells is something also very, very important to consider.
Yes, I'm looking ahead again, and the source of cells, if this kind of treatment in human beings were to continue and move forward, the question is, where do these cells come from? Who donates them?
Yeah, but as you see, now we are moving out of the cells. Now we are going to cell-free therapeutics, and exosomes or extracellular vesicles are one of the type of that therapeutics. So we probably won't need to get cells every time. We will just be able to, with the same cells, get a lot of exosomes, generate that particles which these cells secrete, and use them in.
So from a small pool of cells, you can grow more and more.
Exactly.
This is very exciting, isn't it? And I hear what you say about all the caution and the fact that many more studies are required. You need to be able to replicate what you've done so far and move forward. But this must be quite thrilling for you.
Completely. It's incredibly motivating, obviously, but it's also a huge responsibility. It's a huge responsibility because when you get all this, interest from around, you have to be even more careful with the things that you are doing and what you are saying. So, but I'm very happy because we have now a lot of answers, to many questions, and that's very important.
And of course, heart disease and the failing heart is uppermost in the minds of many, many people around the world. It affects so many families. And I suppose the last thing you want to do is raise the hopes of people unnecessarily, because much more needs to be done.
Exactly, I agree. We have, but we have to keep that hope. We have that hope. I see that. And for me, it's also every time that I'm doing something, I'm trying to check it many, many times, because it's my guide for the next step. So, but what I can say for sure today, that we can keep that hope, that probably not in a very far future we will be able to do great things with the aging.
It's probably an impossible question, but can you put a time on that? You say not in the too distant future.
I think 10 years, it's an important time frame to get important results.
Where do you think we'll be at in 10 years? What will we be able to do?
That's a very hard question, because the things in science, are changing in an exponential way. So I don't want to risk and say something, but I think that things will change incredibly.
We are in the realms of, I know, speculation here, but it raises the question of almost indefinitely keeping a heart at a younger age than it is in terms of chronological age. In terms of the science that you're describing, the prospect there is that you could keep a heart young for many, many decades, certainly longer than nature seems to allow at the moment.
I think that's a very important point, because, of course, the main goal of aging research is not just life extension. We are not looking for a lifespan increasing the suffering of people. We need to get that extra years with a better quality of life. That's the essential thing. And this is what we are trying to do. And not only the heart, but as you can see, a general functional improvement of our organism.
You're talking about increasing health span as opposed to lifespan.
Exactly.
This is very exciting. It's been a really interesting conversation. Thank you very much indeed.
Thank you.
Many thanks for listening.